Hello all, and welcome to Sweating the Small Stuff, a show where we sweat over the details that make our world richer. I'm your personal brain trainer, Cameron Boozarjomehri, and today I'm joined by a very special guest, James Kakalios, who is a physics professor at the University of Minnesota. James, would you like to introduce yourself?
Hi, this is Jim Kakalios. As mentioned, I'm a physics professor at the University of Minnesota, and I'm also the author of The Physics of Superheroes.
And that is kind of a big part of why we wanted to talk to you today. The physics of superheroes is something we always get into on this show, and when I saw your book, when I got to see more of your stuff online, I was like, this is the guy I need to talk to. This is the guy who's going to help me solve the hard-pressing questions. I've
been reading comic books longer than I've been studying physics.
So I imagine you have a ton to share with us. And if you're ready to hop right in, I thought it would be fun to just get a little background on what kind of physics you teach and studied in particular.
So I am a humble but lovable condensed matter experimentalist. So experimentalist means I work in a laboratory as opposed to doing theory. And condensed matter is a fancy schmancy way of saying solid state physics. My research actually goes from the nano to the neuro. We make nanocrystals of one kind of semiconductor and embed them into different other semiconductor films in order to try to make better materials for solar cells or thin film transistors. And I have collaborations with professors in neuroscience where we take the techniques we develop to study electrical noise in disordered semiconductors and apply them to voltage fluctuations in the brain.
So I would like to take a moment and appreciate just how small the things you work with are. Because if you take your hair, if I recall, a hair is a few micrometers across, correct?
Actually, a human hair, average diameter is 100 microns. 1 micron is a 10,000th of a centimeter, a millionth of a meter. Mm-hmm. Basically, a micron is roughly the size of a cell in your body. A nanometer is a billionth of a meter, and it is essentially the length of 3 atoms end to end. If you had a little sphere and it had a radius of 1 nanometer, it would have approximately 200 atoms.
That's mind-blowing to me because this is manufacturing at a scale that is so minuscule, so hard to wrap your mind around that you would think, oh, it's super tiny, so it should be easier to manufacture en masse, but the precision needed is on a scale most people probably can't even comprehend.
And the interesting thing is that the properties of the material change when you make them very small. Because of quantum mechanics, when you put the electrons in a material in a box that's so small that the electrons start to sense that they're in a box, and they can sense the distance between the walls of the box, the properties of the material change. And so if you want to change how well a material absorbs light, it used to be that you'd have to add some sort of chemical impurity to it. But now you can also just simply take, without adding any chemical impurities, changing the size of the material, change how it interacts with light. So really, being able to control things on the nanoscale frees us from the tyranny of chemistry.
That's amazing. First of all, because I absolutely adore how you describe that, but also because I think I have cherry-picked what I hope you will enjoy as the perfect topic of discussion. You probably don't know, but I have been working on a series I've referred to as the scale of life. Basically, in movies and cinema, we like to see things that are suddenly scaled up or down. Like you see Godzilla as this gigantic monster the size of multiple buildings.
Right.
But for today's episode, I thought it would be fun to go talk about one of my favorite superheroes to, I guess, tear to shreds. Ant-Man. I'm sure you're familiar with this guy.
Yes. Henry Pym. No, now it's Scott Lang.
Yes. And so the first episode we did ages ago, back when the world was new and this podcast was young, was about Ant-Man's inability to see.
Mm-hmm.
Basically, as a person gets smaller, their iris would also get smaller to the point where not enough light would come in for the normal human eye to function.
Well, it depends on how small you're talking about. If you're the size of an ant, your iris is still large compared to the wavelength of light, but just. On a human scale, our irises open, several millimeters. The light has a wavelength of roughly, say, from between 200 and 400 nanometers. So Let me just quickly do 10 to the minus
Let's
7.
bust
So
out our
that's
calculators.
about 1/10,000th, 100,000th of a millimeter. So it's like huge compared to the wavelength. Think about water waves coming at the shore, and you have two piers, but they're several miles apart. And the fact that the piers are there doesn't really affect the water waves coming up and striking the beach. But now let's bring the piers in closer and closer and closer. If the piers are roughly the distance of a wavelength of the water waves, the waves will hit the piers and they will reflect off of the piers. They'll collide with each other then and create a diffraction pattern. And what you will see is not just the pure water wave. You cannot ignore the influence of the fact that there are these piers right next to you on either side. So it's kind of similar. When Ant-Man is the size of an ant, his iris is roughly only 7 times the wavelength of light, as opposed to being many hundreds of times the wavelength of light. Now you start to get diffraction effects. You start to get blurring. You get to see double images. So there's two things to note here. One is, this is why it's crucial for Ant-Man to wear his helmet when he's shrunken, because the helmet presumably has eyepieces that correct for this and enable him to see normally. The other thing that's interesting is that in the real world, this is a real world physics problem, and this is why insect eyes are not the same as human eyes. Insects have eyes and different types of lenses that account for the fact that they are on a much smaller scale compared to the wavelength of light. The one thing that doesn't change is the wavelength of visible light. So, but if you're going much smaller, you have a different type of lens. Ant eyes have all of these multiple lenses, and basically what they're very good at is detecting changes in light and dark and any motion. Because typically, on the insect level, they don't use vision in order to navigate the world. They use other senses. They can even sense air pressure with the hairs on their body. And ants' eyes have to do different things than a human eye. The ant is not like needing to read the newspaper or anything like that.
Exactly. And I think, so what I appreciate is the fact that you brought in the suit, because I feel like people don't fully appreciate how much extra work that suit has to be doing for Ant-Man to stay alive.
Absolutely. Yep.
Like, it's not just the vision. I mean, there's another problem, which is if you were either of them, Hank Pym or Scott Lang, and you become super tiny, your ability to breathe in the appropriate number of molecules of air to not suffocate is also changed, because his mouth is only so big and the atoms around him aren't any smaller or any more dense.
You're absolutely right. And this is encapsulated in one of my favorite scenes from a DC comic book, The Atom. Ant-Man can basically only shrink down to the size of an ant, though in the movies he goes down into the quantum realm. But the Atom was always able to shrink down to subatomic size. And in one issue, he and a friend have shrunken down, and they're having a very private conversation as they sit on an electron. And at one point, the friend stops, turns to the Atom, and says, "We're smaller than oxygen molecules. How are we breathing?" And the Atom gives a great answer. He says, "I'm not sure."
It's just superhero physics.
But here's the interesting thing. There is always, no matter how fast you're moving or what you're doing, there is a layer of air next to your body that is not moving relative to your body. And that's a fluid dynamics property, and that's called the no slip zone. And so even when you're moving, like when air is rushing past you, the air is very fast, and then it goes around your body, and there's a thin layer of air around you that's not moving relative to your body. There's a lot of air molecules in that little zone. If you had to take it down with you, shrink it down, and if you shrunk, presumably your clothes are shrinking so that those oxygen molecules are shrinking as well. And so you could actually breathe for a limited amount of time, living off of, in essence, the air that you carried with you in your no-slip zone. More plausibly, the suit has a built-in small air supply that would enable Ant-Man to continue breathing even in the quantum realm.
See, that's the other thing is like, I imagine the suit is doing a lot of stuff that we don't see in the movies. And in addition to probably having some sort of air circulation, depending on how big or small he needs to be, there's also another question of just heat radiation.
Absolutely.
Yeah, the human body, it puts out, we're 98.3 degrees Fahrenheit on average, and that's what our body is. So your cells, and we talked about this in the Godzilla episode that I believe I released before this one, your cells, the mitochondria, are pumping out a lot of ATP, and that means they get super hot.
Yeah.
So your body's ability to radiate heat is a product of your size. You're literally as big as you are, and your cells work at the rate they do because that is the rate that biology has determined is sufficient for you to produce enough energy to stay alive while also radiating enough heat to not die.
Right. Well, and the thing is that the smaller you get, the ratio of your surface area to volume gets bigger. Large objects have a low ratio of surface area to volume, whereas small objects have a high ratio. And so typically, smaller animals that have a high ratio that are warm-blooded, like a mouse, for example, have a large ratio of surface area to volume. It's the surface is where you lose your heat to the surrounding. And that's why those small animals need to eat several times their body weight every day just to stay alive, because they are losing so much energy via radiative cooling because their surface area to volume ratio is large. We are not set up for that. And so there is also the separate issue of an energy drain, depending on what environment Ant-Man is in. If he becomes the size of a microbe and he goes inside the human body, then he's really screwed because he's at 98.6, 98.3 degrees Fahrenheit. All of his surroundings are at 98.3 degrees Fahrenheit. And so if you're at a temperature that's exactly the same as your temperature and you are completely surrounded by it from head to toe, if you exert any effort, you are creating excess energy that you cannot radiate away because you can't radiate it away because it's at the same temperature you are. You can only radiate excess heat to something that's colder than you. So this was pointed out by Isaac Asimov in Fantastic Voyage number 2, volume 2, where Isaac Asimov actually wrote the novelization of Fantastic Voyage back in the 60s. He didn't write the original novel. The movie came first, but they hired him to do the novelization, and he never was very happy with the explanations that he came up with for miniaturization. And so he took another stab at it and basically said, okay, forget that first book, and wrote a new Fantastic Voyage novel sometime much later. And it's pretty cool. And he came up with actually kind of an impossible, but at least it only requires one miracle mechanism by which you could shrink.
And the other problem there is just the fact that, like, let's assume for a moment that Hank Pym and Scott Lang and whoever else is going to be Ant-Man, that let's assume the suit does some amount of radiating for them. That has to be a weirdly efficient suit, even if they are in ideal conditions to radiate heat appropriately.
Absolutely. The suit also, by the way, you mentioned vision. The suit has to correct for hearing. Because now your eardrums are very different compared to the wavelengths that you would normally pick up of sound waves. And if you don't, your vocal cords are essentially a harmonic oscillator, and when you like a pendulum, and when you shrink the length of a pendulum, it just swings faster and faster. So if you didn't want Ant-Man to sound like he was like seriously huffing helium, it's like, hey guys, put that down. Hey, cut that out. I'm serious now. If you didn't want that, the suit's gonna have to also have like a microphone that will shift his voice into a normal registry.
I think this kind of encapsulates the fundamental thing about Ant-Man, which is he himself is a physics quandary, right? Because if you put that many atoms that close together and you do not compensate for mass, like I think you point this out in one of your online discussions where you're breaking down the physics of superheroes. You mentioned how Ant-Man actually isn't changing the distance between atoms; he's changing the density of the atoms.
Okay, so density is number of atoms per volume,
Mm-hmm.
And so he shrunk down to the size of an ant, so his volume is very different,
Mm-hmm.
but his density, the number of atoms, you have a certain number of atoms in your body, and presumably if you shrink down by a factor of 10, then you're 10 times shorter, but you're 10 times thinner, and your 10 times width is decreased. So
Mm-hmm.
that's a factor of 1,000. Now, if your density stays the same, that means I have to take a factor of 1,000 atoms out. So you only now have 0.1% of your atoms. It's like, which ones do you take? And if you take them uniformly out of each cell, you're assuming that the cells can function um, aren't with much less of the material.
Oh shoot! Did I say density? I meant mass. Sorry,
Right,
he's
right, right.
changing his
Yeah. So
mass.
he's got to change. Well, he's got to change his mass because otherwise. But the thing is, he's able to change his mass at will
Mm-hmm.
because when he sits on an ant, he doesn't crush the ant, so he's not his normal weight.
Mm-hmm.
But if he punches a guy when he's the size of an ant, he wants to be able to have more than the force of an ant.
Yeah, he wants that good mass. Yes.
Right. He must have the force. And so I actually came up with a mechanism. How does Ant-Man shrink? I like Isaac Asimov's proposal in Fantastic Voyage 2. The size of an atom, quantum mechanics tells us, is given by a set of fundamental constants. Planck's constant, the speed of light, mass of an electron, charge of an electron, so on. All of these all of these constants have one thing in common. They're constant. They don't change, which is why you can't easily change the size of an atom. So, let's grant a one-time miracle exemption from the laws of nature and say that Pym has discovered a way by which, for example, Planck's constant can be made 10 times smaller. If you look at the size of an atom, Planck's constant shows up Planck's constant squared. So if I make the Planck's constant 10 times smaller, the atom becomes 100 times smaller. So suddenly now I have the same atom, I have the same physics, it's the same distance from the other atoms because they all shrunk, but now they're all 10 times smaller. Now they have the same mass, and so if you don't want that same mass to be in a much smaller volume, you have to interact with some other way to change the mass of the atoms. So Hank Pym presumably discovered the Pym field, which is this universal field that goes throughout the entire universe and determines the size of atoms. The quantum excitation of the Pym field would presumably be the Pym particle.
Mm-hmm.
There is another field that permeates all of the universe that determines the mass of all of the fundamental particles, electrons, protons, neutrons,
I think I
and so
know
on.
this one.
And this is the Higgs field.
Yep.
And the quantum excitation of the Higgs field is the Higgs boson. So the Higgs field, so what is going on, presumably, is that not only did Pym find the Pym field, he refers to it as the Pym particle, just like we talk about the Higgs field, we talk about the Higgs boson, the Higgs particle. Mm-hmm. But not only did he find that, but he found a way to couple it to the Higgs. So he found the Pym field and he coupled it to the Higgs field so that they could interact at will, so he could change the mass of the shrunken object from a low density material, so he doesn't squish an ant when he sits on it, to a much higher density when he wants to punch the jaw of a bad guy. And this, to me, is the fun part of the physics of superheroes. It's not trying to actually explain something that is clearly impossible and is clearly fictional. It's saying, what would I have to change about the universe in order to make this work? And by doing that, I frequently get a better insight into how the universe actually works. To figure out how I would change the size of an object, I have to learn what determines the size of atoms. And to see about how I would change the mass of an object, we look at things that we do know in physics, like the Higgs field. So it's a fun way to get at some real physics, and also helps as an intellectual exercise to say, oh, and there's all these other secondary effects that I'd have to worry about. Like my vision would get all blurry, and my voice would get high and squeaky, and my hearing would get all shifted out. And so, in this way, you think about all the extra things that you would have to take into account, you'd have to worry about. And this is just learning.
Yeah, and I would like to say, I know we're kind of short on time. I'm sorry we had a kind of late start, but I would love to continue this conversation and ideally get to some of the more fun other things, some of them not even in physics that you've gotten to talk about, such as the sociology of superheroes. But for right now, I'd really like to know, I think one of the things I find most fascinating about you and your work is exactly what you're talking about, how you use these superheroes, these incredible sci-fi anomalies as fun thought experiments to really teach the science that you have in your courses, the really making these things tangible for students.
Yes, absolutely. The thing is, physics is, I think, a fascinating subject, science in general. Certainly, we live in a scientific age, but people also have a great deal of insecurity about their ability to understand the material. And so if you can relate it in some way that seems non-threatening, that seems actually kind of ridiculous on the face of it, no one would ever expect that anything associated with superheroes would be scientifically accurate.
Mm-hmm.
And actually, that's one of the beauties. I don't try to look for those places where they get the science wrong. I try to find those cases where they get the science right, because people are so pleasantly surprised when they see that something could actually be right in a superhero movie or a comic book, that moment, their shields go down. And in that moment, you can try to teach them something. But it's a way of basically trying to promote what is going on in science and showing people that these things have relevance. If it works in comic books or superhero movies, it might even be useful in the real world.
Thank you again for this incredibly enlightening conversation, and thank you for taking the time to enlighten us about the importance of not just like physics, but also seeing all the fun places where physics is gotten right in our favorite pop culture, because it, like you just pointed out, it helps us make that knowledge and that theory stick.
Yep. Oh, and I just realized now why you were asking me about the heat exchange of Ant-Man when he shrunk down real small, because that would be a perfect illustration of sweating the small stuff.
Thank you so much for going straight to that joke for me. I think that's a perfect way for us to end. But before we go, is there anything else you would like them to know about? Obviously, people go and find the physics of superheroes at your nearest bookstore.
Not just the physics of superheroes. I also the author of The Amazing Story of Quantum Mechanics, which explains why in the 21st century we were promised jetpacks and flying cars when what we got instead were cell phones and laptop computers. And I talk about how quantum mechanics, while it might be very confusing, is actually a tremendously useful branch of physics. And then my latest book that came out just a few years ago is The Physics of Everyday Things, that follows you throughout your day. You get up in the morning, you turn off the alarm on your smartphone, and I explain how that works. You make breakfast in your toaster. You drive into work with a GPS and an easy pass on the expressway. You go to the airport. You go through TSA. You give a presentation. You go to your hotel room at the end of the day. And while you interact with any technology, from the keyless card entry to your hotel room to the X-ray machine at TSA or the metal detector, I talk about the physics of how this works.
Thank you again, James, for taking the time to talk to us about the physics of superheroes. And if you're listening to this and think you have a friend who would like to learn more about the physics of superheroes, we sure hope you'll share this episode with them, because we found that's the best way to grow our audience, and we're willing to bet they will thank you. As for us, if you'd like to find more Sweating the Small Stuff, you can find us at Small Stuff Show on all social media. We have a YouTube, Patreon, and subreddit, Our Small Stuff Show. And, as always, I'm your personal brain trainer, Cameron Boozarjomehri, reminding you, from movies to media to the world around us, it's details like these that make it worth sweating the small stuff.
Thank you very much.